Okay, let's see. We got a medium today. All right, medium minimum cost path with edge reversals. It's like we're going on to graphs. You're given a directed weighted graph with n nodes labeled 0 to n minus 1, and array edges where edges I is u, v, w represents the directed edge between node u sub I to node v sub I, cost w sub I. Okay. S, U, and V are just the labels 0 to n minus 1. Each node U sub I has a switch that can be used at most once. When you arrive at U sub I and have used this switch, you may activate it. You may activate it on one of its incoming edges. You use V sub I to U sub I, reverse that edge. So directed right, so directed graph means there's like single direction from one node to another node, not like undirected where it's can be where it's like every connection is equivalent. Anyways, you can activate it on same command to change the direction. Okay, and immediately traverse it. The reverse is only valid for a single move. Using a reverse edge costs 2 times W. Return the minimum total cost to travel from 0 to n minus 1 to from node 0 to node n minus 1. If it's not possible, return -1. Okay, n is 4 nodes. You have edges with cost 3, 1, 4, 2. And it's UV. So 0 to 1, 3 to 1, 2 to 3, 0 to 2. Sure, minimum cost to travel from node 0 to node n minus 1. So node 0 to node 3. So in theory, you could just not reverse anything and go 2, 4. Or you go 3 and then reverse this one and do 3, 1. Use path 0 to 1 cost 3. At node 1, reverse the original edge. Sure. How many times can I reverse? That node, I can reverse each node once. I see. Interesting. No reversal needed. It's been a while since I did weighted graphs. How to do this? So example 2 is not only non-visual. I'm just going to ignore it. I think I just need to figure out how to do example 1 correctly. Go to 0, 3. Do. I think it's something like if I think of a backwards traversal, maybe forwards traversal is fine too. From each node to some later node, find the smallest cost. For each node to some later node, find the smallest cost. Track of that. Then how do I consider switching directions? Do I just consider, what if I just ignored, the cost actually doubles, right? I can't just ignore the directionality. I mean, I could go from each node to every other node and just treat the movement as either the original cost with the same with the direction that's given, or double the cost with the direction that's not given, the reverse direction. Yeah, I think that might work. Hmm. Do, 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 do. I think I need like I need 2 dictionaries for keeping track of that stuff. For each node, for each node. So generally, if I use a default dictionary for a graph, the key would be a node and the output would be a list of connecting nodes. Here would be maybe a list of tuples of connecting node and their costs. Sure. Let's say graph is the default dictionary. This will be key is the node, or yeah, one node. The value is the list of tuples, kind of neighbor node, and the cost to go to that neighbor node. So for every, let's say, n1, n2, or xy, so x, I mean, I could use u, v, w. I don't like those letters. I'll use x, y, w. U and v just irks me. In edges, graph at x is going to be, oh, it's going to be a list. It's going to append the tuple that is y and w versus graph at y appends x and 2 times w. So that's just the reverse, right? And then I just build it out, right? I think I build it out using a default, using a heap maybe. Heaps seems like it could work. Because I want to just keep track of the shortest. I want to iterate over the smallest weights currently, smallest total weights. So I think maybe I'll do cost is going to be an array for n plus 1 maybe, or it says n. I think it might be just n. Nodes 0 to n minus 1, so there's n nodes. And this is this will track minimum costs to traverse from node 0 to that x node. I think this should actually be infinity. And then assign cost of 0 to 0, which is to say that it costs 0 to be at node 0 at the start. But since I want to minimize, I want to have a high initial value for the other stuff, and then lower it when I see getting to them at a lower cost. So I think I need a heap here somehow. Heap is going to be a set of, this will be heap of tuples where I have cost and then the node, the cost to get to the certain node. I think that's right. And I think I need to initialize the heap with everything that is that is connected to node 0. So let's wonder, is it ever possible that using this graph in this way, double traverse the same thing? I don't think so. I don't think I ever double traverse the same thing. Okay, let's go ahead and do so I need to go through the initialize heap. I guess it just should be cost 0, 0, right? Cost to get to node 0, 0. Okay, while heap, let's say take the top of the heap, so which is the smallest cost. Cost node is equal to heap dot or heap pop heap, and then for every neighbor node, for every neighbor in graph of this node, then I can do say edge cost comma neighbor. Oh, it's the other way around, right? Is this right? For every neighbor, whoops, this is wrong. Edge cost neighbor. Been a while since I had to think about syntax like this. Edge cost neighbor. No, it's the other way around. Neighbor edge cost. In graph of the node. So look at the graph, look at the neighboring node and the edge cost. I'll say total cost equals cost plus edge cost. I'll say if total cost is less than the cost to get to this neighbor from the array, then I'll say cost to get to this neighbor is equal to total cost. I'll add this to the heap. Heap push onto the heap total cost and the neighbor. That might be it. I think there should be an if statement right here, right? If the node that I'm dealing with is the end node, then I just break here or just return here. If it's not possible, return -1. I guess I return here and return -1 otherwise. Return how is it possible to return -1, to be honest? It's only if like 0 is not connected to the end node somehow. Okay. Return this cost, return -1. Wonder if there's a better way. So this is going to traverse everything. I think that might be fine. So what's this going to do? It's going to push onto the stack 0, 0, and then it explores node 0. It's going to push onto a stack node. It's going to push onto stack neighbor 1 cost 3, neighbor 2 cost 2. And then at that point, the neighbors from there would be 3, 0 is going to be lower cost when I compare it. So total cost is not going to push those push node 0 back in the stack. This should evaluate node neighbor 2 edge cost 2 or cost 2 neighbor 2 first. That's going to push 3. That's going to push 6, 3 on the stack. And then it does cost 3 neighbor 1, node 1. And that pushes 5, 3 onto the stack. 3 is going to be breaking. I think that's fine. I wonder if I should somehow, like if it's like, if let's say 3 was actually not the last node, but there was like a node 4, like n is equal to 5, there's a node 4 that's disconnected here. I wonder if I should somehow prevent it from exploring the second iteration of the node 3. So that could mean either seen, or it could mean a double check here, like if the cost is greater than the cost for this, cost is the, that's poor. Let's say this should be just the cost to differentiate from this single cost. So if the cost currently is higher than the cost of this node, this means it's outdated information. Then I'm just going to continue. Alright, I think that's fine. Costs. Sweet. Okay, not terribly fast compared to others, but I think I might be fine. Guess this might be a little. Just trying to think how I could shorten this. Maybe I could probably get rid of this variable. Just use the expression cost plus edge cost. Sure. Anything else? I think this is pretty useful. I'm gonna have to have this, right? I'm pretty sure I have to have this. Can't just use like a set to see if I've gone to a node, because the node, it's possible that there's a faster method or a lower cost method to this node that I've already seen. So I need to keep track of not the scene, but the minimum cost to that node to see if there's an improvement to be had. Yeah, this is fine. nothing else comes to mind in terms of getting this. I mean, it's possible if there's often a disconnection between the starting node and ending node, that trying to check to see if there's a path from starting node to ending node instead of trying to find the minimum cost is that might speed it up. I don't know. In any case, I'm done here. Summary, kind of this problem is kind of very typical of kind of weighted graphs. Well, I think I could speed it up using instead of default dictionary, just a 2D array here, an array of list. Actually, I'm kind of curious. So it's going to be like a list. So let's try to make an array of lists here. Graph equals list for everything in range n, I want to say. I think that's correct. I mean, hashing versus indexing probably is the same. Oh, yeah, okay. Okay, problem is pretty typical of weighted graphs. First, create the graph using a default dictionary or 2D array where the node equals, or the key, the node is either the key, let's say, kind of the input node, or the starting node is the key or the index, and the output is the value, which is going to be a list of tuples. In this case, it's going to be the neighbor node, and the cost, or you can do cost in neighbor node, it doesn't matter. Then have some other, so build that graph by iterating over the edges given. So that's the first part here. And then to find the least cost to get to the final node, n-1, we'll want to track the min cost to get to each node, as opposed to as opposed to finding the shortest least node path, which would use kind of breadth first search, and maybe a scene set. So here, initialize an array to store those costs. Default is going to be high cost, which is going to be infinity. Compare, which will be lowered during the finding process. And then since we want to always process the least cost seen so far. Makes sense to use a heap instead of a stack or a double-ended queue, and always kind of evaluate paths from the current kind of low-cost path, low-cost node. So here you have your heap. You say initially you're at node 0, cost 0, and then basically when process the lowest cost node in heap by basically heap pop, taking the front. Iterate over all possible or all neighboring nodes from graph, and add those to the heap if or calculate the new cost to get to those nodes. Basically, the node plus the current node cost plus the edge cost, and then add those to the heap if lower than the current min cost to those nodes. So this prevents kind of going over worse paths. To incorporate the reverse kind of reverse operation, make every node traversable, but cost doubled if reversed. So here it's not just x to y, it's a y to x. So graph of x goes to y with cost w. Graph of y goes to x with cost 2 times w. That's just the reverse, right? Time complexities can be O of n, I want to say, where n is the number of nodes in the graph. I'm wondering if there should be n plus like e for edges. Since each node can be explored at most once, really. Well, no, each node can be explored multiple times if there's multiple paths to it, right? Okay, I guess maybe n plus e. And e is the number of edges, since each node can be explored kind of multiple times. Since each node is generally explored once, generally, and each edge is explored once, exactly, based on just the logic of traversing minimum paths. Space complexity, this can be O of n to store the min costs to each node. Actually, it should be O of array and O of n plus e for the heap. I think though, yeah. Yeah, and you have heap might need to be evaluated completely if there is no connection between this node 0 and node n minus 1. Yeah.